Hi, today I'm going to talk about an antenna model I've seen that someone else has made, compare and contrast with what he does versus what I do. This isn't saying any one way is better or worse. It's just talking about basically the differences. Give those who have seen what I do and how I do it a different perspective of using a program like this. The person is KP4MD. You can find this page at qsl.net/kp4md/modeling.htm. And actually, you can go just to the qsl.net/kp4md. He has other pages talking about different antennas and has different models. The first thing on this page that I don't like, on this model, that I don't even have to bring up my software to show, is the blocky look of the models. He's running the model at the default setting of every 5th degree. I don't really like that. When I see that, the first thing I think is noobish mistake, which I actually thought on these. Luckily, I have looked in further, and I don't think it's a noobish mistake. I just think it's a single step that he hasn't taken that would actually increase the accuracy and increase the look of the models as well. A much smoother look just looks better. I've shown how to do that before. I will show that again in this video. So let's actually, I want to bring this up, and here we see I have the same model. I'm running the 2-meter version of it. 4.23 dBi gain, 4.23 dBi gain. I can put it right next to it. It looks the same. It's the same model. It's literally, he made it available on the site. You can get it right here, 80 inches above ground on metal mast. I took it, I basically pasted it into a NEC file, and that's how I got it. So anyone could go to this site and get this or any of his other models. He has other models here talking about different antennas. I know there's other antennas on other pages on this part of his site. I don't know if those are all available, but he has made a lot of these available, which is something I like. I'm going to go ahead and minimize this because I'm done with that part for now. Let's go ahead and run this again to... No. Here's the antenna itself after the layout. What I'm going to talk about is, I'm going to call it the hub here. I'm going to open up segments. This is something that I've known about, but I've never actually used. The methods that I use in this are not easily compatible. But across here, we see we have wires attaching, but we see the endpoints are darkened while the individual segments are just the individual circles. What we have is, what I would do if I were to make this is make a wire here, and a wire here. I would do that mostly because I use the program's built-in auto segmentation feature, which he clearly has not. There's nothing wrong with not using it. I actually like his auto segmentation solution for this, and I'll go into it a little bit later. It's definitely one of the things that I do like. But this is something that shows that you can actually attach to a wire. If you know where a segment endpoint is going to be, you can actually attach wires to that segment endpoint. And I believe you can actually attach segment endpoint to segment endpoint. Or segment point to segment point. So I could actually put, if I had two wires forming an X, I could put this wire going down further. As long as they both had a segment at the same point, the software would treat them as connected. It's not something I see very often. As a matter of fact, I think this is the only time I've ever seen this. I knew this could be done, but it wasn't interesting to me because, as I said, the ways that I do this are different. So this is just an interesting use of an aspect that I don't really use. So let's zoom that back out. Turn the segments off. Like I said, I use auto segmentation. So now if we go into here, this is where the wires are set up. And as I said, he uses his own form of segmentation. We have one of them, this crossbar here, the wire number 2, that's this one that's specifically 3 segments long. We also can see that it goes from 0 to JS, 0 to minus JS on the x-axis, so it's a variable, which is something I also like that he uses. The variable length of JS, which is 4.5 inches. And what he does is he takes that 4.5 and multiplies it by 3, because each segment will be 1/3 of it, because there's 3 of them. And then he divides the overall length by that figure. And what that does is, it, as I said, it gives him an auto-segmentation of sorts. It'll work very similar to how auto-segmentation works. As you make these elements longer or shorter, it will add and remove segments as needed. Definitely something I like. Again, it's not something that I would normally use, but it shows something that is capable, that the software is capable of handling. If you'd like to use that rather than the built-in auto segmentation, that's up to you. It works well with the specific way that he built this crossbar down here. So I have to say they work extremely well together. Another thing I like, if we click on the source and load data, basically wire conductor, aluminum, but the tag is tag 0. When I did a video showing when I was using copper wire, I did one for each of the wires. And that's habit for me. I've done that for a long time before I realized that you could do this. So it's just habit. But you can actually go in and put tag 0, and it will apply it to every element on the antenna. So if you have an antenna that's going to be all aluminum, here you go. One line down here, and if you have 10 different elements making up the antenna, you have one line here. And it doesn't matter if you add or remove. Everything will just always be aluminum. And getting back, he used variables. I like using variables. It makes it easy to adjust things. Plus, you can go into an optimizer. You can actually make it changes that way. It just makes it easier to work with the antenna, especially some of the more complex antenna models where you may adjust a variable. Like here, I can adjust the antenna height. In this case, it's the M. He calls it for mast. You make that longer, that will actually adjust the height. The way he designed it, that will adjust the height of the entire antenna. I like touches like that. It makes it easier to work with the antennas after you do it. I don't have to go change something for however many wires I have just to do something simple like change the height. Now a few things I don't really like. Again, starting with where we started from. I don't like how blocky this is. All you have to do is, I press F7, but you can also go under, let me exit this, you can also go under Calculate and the NEC output data that comes into here. All you have to do is change this RESOL, resolution is what it means, to 1 degree. You'll note we start with a gain of 4.23 dBi. And once we run this, we have a gain of 4.32, and it looks much smoother. As a matter of fact, if we look for peak gain, we'll notice it is actually not on one of the 5-degree lines, which is why we're getting additional gain out of it. It's actually over here. It's actually at 9 degrees, not the 10 degrees where it would have shown up as peak gain on the model that he used. I just think these look cleaner. It gives you more accurate information. The reason it was 5 degrees by default to start with is because the NEC 2 engine was originally meant for really slow computers. You don't have that issue anymore. Computers these days can handle 1,000 times over what they could before. So increasing it up to every 1 degree from 5 degrees doesn't really, as you saw, it didn't take much time at all on a modern day computer. And this is an old computer. This is a good 6-7 year old computer. I'm going to set that back to show something else. Oops. We're going to run something called AGT, or average gain test. We're looking up here on the screen, AGT results, 0.902. This antenna is underreporting gain. It actually tells you approximately how much it's underreporting gain right next to it, which is minus 0.4 decibels. In and of itself, by itself, this isn't necessarily that bad of a thing. I tend to like to be a bit more accurate when I show outputs. I will adjust AGT to be 1 as much as I can, and if I can't, I will get it as close as I can. There's been a few models I haven't been able to adjust to get right at an AGT of 1. But if you're taking this model and you're comparing it to, say, a different model, and you're comparing two different antenna designs, if AGT of 0.9 to AGT of 1. I forget the high range. I think it's 1. Well, whatever the high range is, you can actually get a pretty big range to where one will underreport, one will overreport. And if the overreporting one has less gain, it might actually look like it has more gain than the other antenna that is underreporting. So it's not so big of it doesn't make that much of a difference here. But if you're doing comparisons, you definitely want to make sure the AGT results for both antennas are consistent and in line with each other. They don't have to be both at exactly 1 like I tend to like to use. But you do want them to be consistent. So if they're both at 0.95, then they're both at 0.95. Another thing, I used to have a cheat file for what the reference was for the AGT results. This might be used. It would say in this case for an AGT this low that it might be usable in some cases, but is not accurate. If AGT was just a little bit lower, the AGT results line there would be red, and would definitely be considered not accurate. So we're basically borderline accuracy on borderline usable for this antenna. One other thing I'm going to go into, it says comment, under his comments, simulated good ground. Well, I went in and I took a look at the ground. User specified conductivity 0.01, dielectric constant 4. Now if you go into good ground, it's way up at the top, conductivity 0.015, dielectric constant 17. Now I'm going to go, I don't want to save that, so usually anything that has a dielectric constant of 4 would be considered a poor or moderate ground. I don't know why he's using these and calling this simulated good ground. Maybe he has done some testing that I don't know about or don't have information on that specifically states that this is good ground for 2 meters or 440 megahertz band. I don't know. So on this, I am suspect. And that's pretty much it for this model. One other thing I like is instead of putting in an individual frequency, he did FRQ. That actually gives me as a workaround in Linux where you can usually go to frequency sweep and set it up to run through frequencies and give the SWR data like he has on his site and other data there. That doesn't work so well in Linux. It's bugged. As I run Fornac 2 in Linux, I'm usually running through something called Wine. Running the frequency suite right from the main thing doesn't seem to do this, but I can go into the optimizer. I'll show you that here. Let's go back to 1 degree here. Oh, I'm still in AGT. see if I go into frequency sweep, doesn't matter what I have in here, generate. Usually it doesn't, oh, this time it did. Usually it doesn't give me this window. This time it did. There's a few other bugs I've had. You'll also notice gain is minus 0.39. So it's giving me this window. What if I were to go in and he's from 140 to 150 megahertz. Let's make it step 0.5 megahertz, so 2 each. It's working. Usually it doesn't work. I don't know why suddenly it is. But usually it doesn't work, and even when it does work, this is giving me modeling data that very closely matches what he has here. This is sometimes way off. I don't know why it's working at this point, because usually it doesn't. And what I've been having to do to get it to work consistently is come into the optimizer. I pressed F12. You can also go under Calculate, Start Optimizer. And what I would do is run sweep frequency, punch the data in, and we're going to go 20 steps. It would go through and run that. Oh, it didn't bring it up this time. Well, as you can see, this software is kind of buggy in Linux, so I've had to do things to work around. But usually I do it this way, and I get the results that I was just looking at. I don't know why I'm suddenly not. Actually, I think I'm still in frequency sweep. That might be why. Let me turn that off. Far field pattern. There we go, F12. I change this to sweep. I don't like the optimized side, but I love sweep. I use that all the time. We're going to 140, 150. We're going to do 20 steps between. And the sweep. There it comes up. This way it comes up all the times. If I do the frequency sweep as I did before, sometimes it doesn't come up. There is one other thing I don't like about this file. There's another bug in using the software. Like I said, it's buggy when I'm running it in Linux. But unfortunately, I don't have any computers that have Windows on them anymore. And I really have no interest in going back to Windows. So I deal with the bugs. We're going to look at I'm going to pull this over here. You'll notice we have a wire going all the way down, connecting directly to the Earth. If we actually look in the geometry, that file on height goes all the way to 0. Where is it? Yeah, it goes all the way down to 0. So it touches the ground. Now, it's touching the ground with real ground. This doesn't actually work very well. If you do something like this in another program called EasyNet, it will actually give you an error message saying that it is not accurate. That being said, EasyNet also calls a different ground. It calls it calls it a high accuracy ground, which is real ground here, and it also has something called MiniNet ground that it also calls real ground. If you have a wire touching the Earth directly, you need to use MiniNet ground. There are reasons for this. The main thing is the fast ground and the real ground don't handle that connection to the Earth properly. What they see is a very small part of the wire touching the Earth. They don't see anything underneath, like a ground rod or anything like that. So they don't actually properly mesh the antenna to the Earth, and it actually gives you incorrect information. MiniNet ground kind of resolves that. I should probably go through and do a video talking about the different grounds. MiniNet ground kind of resolves that because MiniNet ground treats any connection to the ground like the ground is a perfect ground. It doesn't give you perfectly accurate data, but it gives you more accurate data than fast ground or real ground. So if you have a wire touching the earth, you need to use mini net ground, and you need to realize it is not 100% accurate. I have read somewhere about a system that someone used. What they would actually do is, at the area right before it touches the ground, they'd put a resistive load on there. And that would actually simulate a 4 or an 8 foot ground rod. They had formulas for that. And unfortunately, I can't find that. I don't know what happened to that information. But I wish I still had it. And that will actually give you more accurate data for what's happening with the ground interface than the mini net ground will. Because like I said, mini net ground treats it like it's a perfect ground, which is not what it is. Well, that's what I like and what I don't like. If anyone else has any comments on these, or has likes or dislikes of their own, or perhaps the person who made these happens to see the video, I'd love to chat with you. I have certain questions about how and the why you do certain things. Love to have a discussion with you. Maybe I could help you out too. Thank you.